Hello everyone and welcome to the webinar. My name is Josh McDaniel. I work with the Wildland Fire Lessons Learned Center, and I'll be the facilitator for the webinar today and sort of moderating the question and answer session. But first I want to make a few quick announcements and get a few of the technical details out of the way. This webinar is part of a larger series that we've been doing for a couple of years now, and it's a collaboration between the Joint Fire Science Program, the International Association of Wildland Fire, and the Wildland Fire Lessons Learned Center. We usually have one or two of these a month outside of fire season. We'll probably a little less regularly during fire season, maybe once a month during fire season. And so we're starting to fill up the spring schedule for the webinars, and hopefully you can see that there on my screen, but we've got a really good set of webinars coming up, and these are all part of a series of webinars on extreme fire behavior. That's part of a synthesis of research on extreme fire behavior that JFSP has sponsored. And so you can see there's a couple presentations by Paul Worth coming up in February on critical weather patterns in North America and Australia, I believe. Yep. And then in later February, Brian Potter is going to be talking about fire columns and plume dynamics, and then in early March, Brian will be speaking about spot fires again. One thing I like about this series is very nice, simple, plain titles. I love it. Okay, so everybody's complained about that. Their titles don't match the content in the past. So what you see is what you get here. All right, April, Scott Goodrick and Jason Forthofer will be talking about vortices and wildland fire. And then May 7th, Marty Alexander and Miguel Cruz will be talking about crown fire behavior and conifer forests. There's a few more that we're trying to include in there, including one on there's another webinar in the smoke science series coming up that we're trying to get scheduled at the same time. Okay, so a couple things about the webinar for today. Most importantly is questions. If you have a question, type it into the questions box in your control panel. We're going to save questions till the end, and we'll have a Q&A session, and we'll try to get through all of them. There's a lot of people in this webinar. There was close to a record registration number, I think 400 or so people registered. Looks like we've got about 218 people in the webinar at present. So there'll be a lot of people here. There'll be a lot of questions. So if you have a question, get it in early so that we make sure we get to it. Also, the webinar is being recorded. There will be a recording of it available. I've tried to upload it as quick as I can, an hour or two after the webinar. And you can find that here. Let me slides. Okay, the Advances in Fire Practice page, which is one of the pages in the Lessons Learned Center's website. So if you Google Advances in Fire Practice, you can get there. You can use and navigate to it through the Lessons Learned Center's websites. And right over here to the right is where the upcoming webinars are, and you can register for all those webinars that you saw earlier if you don't get the emails announcing them. Okay, with that I will be quiet and let the presenters take over. But first I want to introduce them. Two presenters today, Craig Clements and Neil Lareau. And Craig is an associate professor of meteorology and director of the Fire Weather Research Lab at San Jose State University. He teaches courses in meteorological instrumentation, mountain meteorology, and fire weather. He received his PhD from the University of Houston in 2007 and received the NSF Career Award in 2012. Neil Lareau is a postdoctoral research associate at San Jose State and studies fire-atmosphere interactions and plume dynamics of active wildfires using a novel mobile Doppler LiDAR system. That's a tricky little word combo. Dr. Lareau received his PhD in atmospheric science from the University of Utah in 2013. Okay, with that I will hand it over to Craig and Neil. Oh, wrong one. Here, let me hand that one to there.
Okay.
All right, looks good. I can see it. Yep.
Okay, great. All right, everybody. Thank you so much, Josh, for the introduction. We are going to talk today about a document called The Synthesis of Knowledge of Extreme Fire Behavior, Volume 1 for Fire Managers. And this came out of a Joint Fire Science Program project with a number of authors, as Josh mentioned earlier. And our topic today is Chapter 2, which is the effects of complex terrain on extreme fire behavior. And again, I'm Craig Clements, and Neil Lareau and I will both be presenting this presentation. Outline for today is we're going to cover some wind systems in mountain terrain. A lot of this might be review for people, but we're going to take a look at some new observations with our Doppler LiDAR of valley winds and look at dynamically driven winds and some cases of Santa Ana's and the Washoe Zephyr in the eastern Sierra. Then we're going to talk about fire behavior on slopes and canyons and kind of some eruptive fire behavior and atypical lateral fire spread that's been observed in recent wildland fires around the world. Let's see here. I'm trying to, I might click through. There, and then we'll finish up with some observations of plumes in complex terrain and then finish with some take-home points. So we do want to recommend some textbooks for the general knowledge of mountain weather and climate and mountain meteorology. One is Mountain Meteorology by Dave Whiteman at the University of Utah. It's an excellent text. It talks a lot about the circulations. Another text which is very good is Roger Berry's Mountain Weather and Climate. And so a lot of the figures come out of Dave Whiteman's book that we'll be presenting today. So a quick overview. Lateral mountain winds develop over complex terrain of all scales. They're characterized by a reversal of wind direction twice per day. They're strongest with clear skies when winds aloft are weak. And as a general rule, upslope and up valley winds occur during daytime and in the opposite direction during nighttime. They're produced by horizontal temperature differences and resulting horizontal pressure differences. So here's a nice schematic from Dave Whiteman's book showing both the slope wind system, the along valley wind system, and the mountain plain system. So during the day, you see the circulations of upslope winds on the sidewalls of valleys, whereas the valley wind goes up, and there's a return circulation on the aloft as a result. At night, the circulation reverses with downslope winds, down valley winds, and such. And there's also a mountain plain wind system where winds blow to the mountain during the daytime and away from the mountain front during the nighttime. So looking at some observations, this is from Tuolumne Meadows. This is a RAWS station at the meadows, and what you pick up immediately is that there's a real strong change in wind speed. So during the day, winds are approaching 6 meters per second. At night, they're about 1 meter per second. And you see this pattern all through this 10-day period of observations. And you also pick out that during the daytime, winds are from the west, and they shift abruptly to the east, which is down valley in the Sierra Nevada, shift abruptly to the west again. Whoops, my mouse is messing up here. And then back. So there's this clear diurnal pattern of up valley, down valley, up valley, down valley. So very classic in structure. If we look at the vertical profile of the valley winds, again from Tuolumne Meadows, this is a Doppler SODAR profile, time height plot showing vectors. So the direction of the arrow is the direction of the wind, where it's coming from as if you were looking on a map. So these are easterly winds here at the surface here at 0 to 6 a.m. in the morning. And then, so there's a low-level jet. Strongest winds are near the surface, lowest 100 meters. They become near zero, and then they shift to the synoptically driven southwesterlies. But what I bring your attention to is that by mid-morning, the regime changes, and we go through a wind shift where winds begin to blow westerly or up valley. And then they strengthen throughout the day. And you can see that throughout the whole layer, they're well mixed or fairly constant with height up to almost 600 meters above the ground. This red line here indicates a region where there's decoupling occurring. So as the cooling begins in the evening, you get your drainage winds or down valley winds, very light initially, but they're decoupled from the up valley winds, which still exist aloft. And so this wind shear can present episodes of turbulence where you might get some winds mixing down from the aloft to the surface, especially during periods of wildland fire where the plume can interact with upper level winds, mixing this momentum or wind down to the surface, which is complete opposite direction from the surface winds. Okay, so we're going to show you a lot of observations today, both of fire plumes and of winds using what's called the mobile Doppler wind LiDAR on a truck-mounted platform. So we have a LiDAR, a microwave profiler, a radio sound system. We take this out to wildfires throughout the western U.S. And so the LiDAR basically is full scanning like a radar, but it uses a laser beam, and so it basically gives us aerosol backscatter so we can measure smoke, but we also get velocity data, radial velocity from the LiDAR. And we can do all sorts of profiling mechanisms. We can measure the CBL depth, the wind profiles, and such. And so an example of that is some measurements that we made in Yosemite Valley in 2013 during the rim fire. So we were positioned over here at tunnel view, and we were scanning across the valley like this. That's what the square box is highlighting here. And so we were measuring the up-valley winds. And what we want to illustrate is that there's a lot of horizontal variability of the valley wind structure. And if we look at a loop of the LiDAR here, so you can see the reds are winds blowing away from the LiDAR and greens are winds that are zero. So there's lots of variability in the wind structure across the valley. Usually you think that the wind's probably constant in the valley, but it's not. There's a lot of acceleration along the sidewall here, and there's stagnation along the other sidewall. So this is just horizontal scans across the valley here. And what you're seeing, the reds are away and blues are towards the LiDAR. So you'll see that throughout the presentation. So if we take a time average of that, we see that the wind accelerates around the corner on this side of the valley, but it decelerates or weakens around this side of the valley. So this variation can have impacts on fire spread on the valley floor or in any mountain valley for that matter. This is just a good example of a mountain valley and a mountain range here. So next slide. Another thing I want to talk about, which was mentioned in the text, is inversion breakup in mountain valleys. This has been studied for many, many years, but this is an example from Lee Vining Canyon in the eastern Sierra Nevada. And what the take-home point is that during inversion breakup, rapid changes in wind speed and direction can occur. So for example, these are tether-SON profiles, so a potential temperature, water vapor mixing ratio, and the up-valley wind component. So negative values of the wind are down valley, positive values are up valley. The time is here in the inset box. And so what you see is that we have a real strong temperature inversion in the morning. This is typical of most mountain valleys. It's very shallow. And if you look at the wind speed over here in the other plot, you see that the winds are nearly zero or close to ½ meter per second. So a very gentle breeze, very decoupled. So you're in this what we call a cold pool. Within a matter of hours as the sun rises, the inversion breaks and we get a constant potential temperature which infers a mixed layer developing. And so at the same time that happens, the winds shift in direction and they can increase at the surface rapidly. So we went from basically zero winds at the surface within an hour and a half to 2 hours, winds at 3 to 4 meters per second near the surface with much stronger winds aloft. So this is the transition period that is always a lookout situation when you're in a mountain valley. I'll let Neil take over this slide here.
Yeah, so what we're going to do now, Craig kind of laid the groundwork for these diurnal transitions in both temperature inversions and up valley and down valley winds. I'm going to show you a couple of LiDAR sequences from the King Fire, which was here in the Sierra Nevada this past summer. So this first one's going to look at the evening transition period. The LiDAR is situated over here and pointed across the American River Canyon, and the fire is actively burning on the far slopes. This is kind of a rough estimate of what the valley profile looks like. So I'm just going to go ahead and turn this loop on, and what we're looking at is the backscatter from the smoke. So before sunset, there's this active convection occurring, but sunset is around here. You'll start to see a rapid stabilization in the atmosphere, and as a result, the smoke becoming trapped in an inversion layer right there. Now you can clearly see the inversion setting up. What's quite notable here, though, is further up on the slopes. Well, let me just annotate this a little bit. So here's the inversion layer. So as the stability sets in, it kind of shuts off the convection and the fire activity in the valley. But up here in the so-called thermal belt, where you're above the valley inversion that's forming, you're able to maintain some more active fire regime. So this is that kind of layer that Craig was showing from the Tuolumne Meadows data of the winds aloft and kind of a different regime above the surface-based inversion. There's also evidence of a down valley jet here, which is actually flushing the smoke out of the valley at low levels. So it's injecting clean air into the valley and flushing that out, while the smoke from the fires up on the slopes is remaining trapped within that inversion layer. Just kind of a nice example of that evening transition and quick changes in fire behavior. We can also look at the morning transition from the same location, same valley on the King Fire. I have a sequence of photographs here where we have down valley flow in the morning. The flow is all going kind of away from the viewer here, down the canyon. Then progresses into an inversion breakup phase. Then towards an upslope phase where the fire is making quick runs up the lateral slopes. And then finally in the afternoon, the flow comes around and it's totally up valley. And then the fire is progressing up valley toward our observation point. We were able to capture this transition with our LiDAR as well by pointing it down the canyon. Oops, go back here. Scanning through the night. So the LiDAR is over here and it's looking down the canyon, and we're seeing smoke from kind of backing fires overnight, and it's all being ejected down the valley, everything to this direction. You can see it being swept away in that down valley nocturnal flow that persists into the morning. Now we're getting into the transition period. You can see the convection starts to get a little deeper. We also shut off that down valley flow, and then all of a sudden it comes around, it becomes up valley into the afternoon. We'll start seeing the fire make much more rapid progress in the up valley direction here. There, big jump in the fire position, and starting to spread smoke up into our area. And another thing that happens in these afternoon transitions is as you go from the decoupled morning into the coupled afternoon, so you can interact with the synoptic flow aloft, which is the strong winds driven by high and low pressure systems. So in this particular instance, we see these typical diurnal transitions then give way to coupling with strong southwesterly flow, which in the case of the King Fire created this rapid expansion in fire along the direction of the synoptic southwesterly flow. You can see both in terms of the smoke plume here from space. This is a MODIS image. And then this is an image taken from aircraft where we have these really strongly tilted over plumes that are contributing to long distance spotting and rapid fire growth. So just kind of an illustration of that decoupling, recoupling, and then interaction with synoptic flows. Next we're going to talk about some dynamically driven wind systems. And the two that we're going to talk about are the Santa Ana wind, which most of you probably know affects Southern California, and also the Washoe Zephyr, which affects the Eastern Sierra. So an example of the Santa Ana event from 2003 here on the top, and then some Eastern Sierra fire activity here. So the Santa Ana winds can be driven both dynamically and by temperature differences. So one of the typical setups for Santa Ana winds is an upper level ridge to the north and an upper level trough to the southwest, something that might look something like this idealized schematic where we have a ridge over northern California and Nevada up into Oregon and a trough off the southwest coast down here. And this will set up a pressure gradient that drives strong winds out of the Intermountain West across the coastal topography. We can also have cold air outbreaks in the Intermountain West that become dammed up behind the mountain ranges and then spill through the gaps, and this can contribute quite a bit to Santa Ana flows as well. And regardless of the driving mechanism here, the outcome tends to be strong winds and dramatic warming and drying at the low levels in Southern California, which then contributes to extreme fire behavior. And just as a note, we had an event last week, and this is kind of the classic setup for Santa Ana's, where we have the ridge to the north kind of folded over on top of a cutoff low to the south. You can see the stronger flow right through here, and there's some strong winds in Southern California just last week doing a little bit of damage. So one of the things that happens with Santa Ana winds is we often see a sudden, not a sudden apparently, a sudden onset of warming and strong winds. So this is an example from 2013, October 2013. The top panel shows the wind speed in blue. You can see this rapid jump in the wind speed up to about 10 meters per second, or about 30 miles per hour. You can also see a strong shift in wind direction where the winds become easterly. This has to do with that flow punching through the gaps. We see a dramatic surface warming, go from kind of the mid-50s up to the mid-80s, and then a rapid drying, this drastic drop in relative humidity. So there's the sudden onset. So what causes the wind to accelerate and bring these strong winds to the surface? Well, there's two primary mechanisms. The first is gap flows, which is the cold air penetrating through gaps. An example of some gap flows up in British Columbia here. And another case is what we would call something like a hydraulic flow, which is more like flow of water over a dam, where you have dynamically driven flow across a mountain barrier, and as it descends the lee slopes, it accelerates dramatically, penetrates down to the surface, and can cause quite a bit of mixing. And one of the things you'll see with most Santa Ana events is that they're typically focused on gaps in the coastal mountains. So there's some combination of these two processes going on in most cases. So that's what causes the acceleration of the wind. So what causes the warming and drying? Well, there's two processes that we can implicate in that. And the first is downslope flow, which is the subsidence or winds descending in elevation. And that's going to cause adiabatic warming, which tends to occur at 5.5 degrees Fahrenheit per 1,000 feet. This is the dry adiabatic lapse rate. And that warming, as it comes down to the surface, will then drive a strong decrease in the relative humidity. It's often also associated with a decrease in the dew point because you bring a drier air mass in out of the Intermountain West. But what I'm going to focus on for the next couple of minutes is a slightly different process, which is the marine layer removal. So typically in coastal California, there's a marine layer that resides downstream of the mountains on the Pacific side of the mountain ranges. And when these strong winds come across the barriers, they can actually erode and displace that marine layer. So not all of the warming is just due to this adiabatic process, but because you're displacing the marine air off of the coastal mountains. And that's going to lead to a rapid change in surface temperatures and usually a wind reversal as well. So we were fortunate enough to get some observations of one of these events. This is another LiDAR image looking at the radial velocity. I have it kind of annotated here. This is at the onset of a Santa Ana wind event. And so the blue to red here above the dotted line shows flow from the east. So strong flow at about 15 meters per second. Down here at the surface in the marine layer, we have reversed flow, and you can see this inversion separating the two. Over the course of the morning, you can see the strong winds mix down to the surface. So this is a top-down erosion of the marine layer. You can see that quite nicely here. So this is a little bit different than the typical inversion breakup scenario that we see in mountain valleys, where there's often this kind of convective bottom-up approach at removing the inversion. So this is a mechanically driven mixing from the top down. You can also look at this in terms of the time evolution of the wind speed above the LiDAR, and showing more or less the same thing, that the marine layer gets eroded from the top down and eventually intersects the surface. And right when it intersects the surface, when we get a big jump in the surface winds and surface temperatures. So this would be the onset of your critical fire weather conditions at the surface. So this may have been going on aloft above a given location, and over the course of the event work its way down, and then bam, all of a sudden you have a very different scenario at the surface. We've also looked at this using large eddy simulations to understand the dynamics of what's going on here, and I won't really belabor the point too much, but this is a simulation showing the removal of an inversion by strong winds. You see the strong flow coming across the top of an inversion contained between two mountains. And all of these waves develop, and these waves are what's mixing out the surface-based inversion and giving this reduction from the top down over time. This inversion will just continually thin and thin and thin as it makes its way down toward the surface. Jump out toward the end here. There we go. We've removed most of the inversion. You can see all the wave mixing going on, and then complete flushing of an inversion layer. And this would be, again, the onset of the strong Santa Ana winds. So just a couple of take-home points from that. The warming in Santa Ana winds is caused both by descending air, but also the erosion and displacement of the marine layer. The onset can be sudden at the surface. And one of the things that we've seen in our work is that the timing of inversion breakup can be quite difficult to predict, and there's a lot more work required to really pin that down. But it's quite important because it's going to drive rapid transitions in fire behavior. And what we're hoping to do with our instruments is to provide some more real-time in situ data to help resolve the timing of inversion breakup. So I'm going to hand it back to Craig now, and he's going to talk about the Washoe Zephyr.
So there are exceptions to the rule when we're thinking about mountain wind systems. You know, during the day, winds blow up the valley. During the night, they blow down the valley. Winds don't always blow up the valley during the day. And in particular, in the eastern Sierra Nevada, a daytime down canyon wind blows regularly, especially through the spring, summer, and fall. And that has been termed as the Washoe Zephyr. And here's kind of a schematic, idealized cartoon showing what it looks like. So you'd have winds that are blowing towards the Sierra in the afternoon, and strong down canyon winds flow over. Now in the morning, we have up valley winds on the east side, but they are replaced by the down canyon winds by late afternoon. And we've done some work with this, looking at the climatology of the Washoe Zephyr. And so I don't want to go into too many details, but we looked at the climatology for multiple sites: Reno, Galena, Little Valley, Mono Lake, and Lee Vining. And what this plot shows is the frequency distribution of winds from the northwest, southwest, so westerly quadrant as a function of year and hour. And it looks, the highest frequency occurs, let's look at Lee Vining down here, during the late afternoon. And this is due to a pressure difference that develops in response to thermal heating between the Great Basin and the west side of the Sierra Nevada and the Central Valley of California. This plot here is the frequency distribution of just westerly winds that are greater than 5 meters per second, and we see that they occur between 1 to 2 p.m. to 7 p.m. locally. So this is a very strong wind, typically between 5 and 8 meters per second in the afternoon, down canyon, eastern Sierra. I'm not going to go into too many details of this plot, but what the red line shows is the wind speed at 700 millibars. So this is the upper level winds. So at any given day, or on these 90 days here, 3-month period, this is the surface data down here in the bottom panel, and the shaded bar here is meters per second. So what we see is that even if the upper level winds are strong or weak, they don't correlate with the winds at the surface. So on this day here, we have winds that are less than 5 meters per second, but yet we have winds about 8 meters per second at the surface occurring in at 5 p.m. in the eastern Sierra. And this is very common. Folks in Reno know this phenomena, but it does provide a mechanism for extreme fire behavior in the afternoon as this thing develops. And so real quickly, the mechanisms are basically caused by asymmetric heating between the Great Basin and the west of the Sierra Nevada. It evolves during the daytime. A regional pressure gradient then allows the air from the west to cross over the crest and flow down the eastern slope in the afternoon. And here are some numerical simulations that were conducted as part of the study. And you can see that in the afternoon, the strongest winds occur on the eastern Sierra here. And you can see that they're flowing up and over and then accelerate down canyon on the east side. So this is a unique situation that could really drive fire behavior downslope afternoon at high rates of spread. The next section of the talk will be looking at fire behavior on slopes, and I really want to talk about eruptive fire behavior and lee slope effects, and talk about work of others, particularly some laboratory experiments from Domingos Viegas of University of Coimbra in Portugal. Here's a picture of some slope fire spread. So this was ignited at the bottom of the canyon. This is Henrico State Park in 2008. And you see that there's no ambient wind. Basically, it's post-frontal, but the plume is going vertical here. But if you look in the canyon, the smoke is not going vertical. It's actually being entrained up into the top of to the base of the column, but it's being trained along the slope. So this is this fire-induced entrainment on the slope that we'll be talking about a little bit later. And so it's this circulation that develops that helps spread or accelerate fires upslope, along with the geometry of the terrain as well. So starting off with eruptive fire behavior, Viegas 2005 proposed the term fire eruption given the similarity between the convection column of a volcanic eruption and that of a wildfire as the wildfire's rate of spread accelerates. It's also been called blow-up fire behavior. And fires on steep slopes and in canyons in particular have a behavior where the rate of spread increases continuously, producing this fire eruption. And I'll show you some examples of that with some of the work that's been done. And so one other point that Viegas has made in other papers is that fire eruption in canyons is not rare. This occurs in most canyons, that the spread rate continuously increases. And it's also been associated with major fatality fires throughout the world, both in Portugal, Spain, and the U.S. So here's a list provided by Viegas and Simeoni in 2010 where they did a review of extreme fire behavior in canyons. So most of the work that has been done has come out of the lab experiments conducted by the University of Coimbra and Domingos Viegas. And so he has an elaborate setup in his laboratory where he can adjust the terrain to match any configuration and tilt angle. So as you can see, here's a little ignition. These slides were provided by Professor Viegas. And you can see there's an ignition here through this fuel, and it continues. And then within just a few seconds, it explodes, and you have a rapid rate of growth on both sides of the canyon. And so from the lab results, his team developed a semi-empirical mathematical model to predict rate of spread of the headfire in canyons. The model has been applied successfully to interpret real cases and also applied to different fuel types. And it has assumed a fire-induced wind that modifies the ambient flow. And this is based off the idea that the convection modifies the flow within the canyon. And so looking at some of the model results from different topographies, this is from Viegas and Pita, 2004, so different canyon geometries using that analytical model. And why the term explosive is so appropriate is that within just some seconds here, as the fire is going up the terrain, you can see that the area growth increases rapidly after a little bit of time. And so in all cases, no matter what the terrain. And so looking at different slope angles and also canyon floor angle as well. Numerical simulations from Clements et al. Using the FireTech model also show similar behavior. And I don't want to go into too many details here, but give you two examples. So there's a narrow canyon simulation, that's this side here, and a wide canyon. So two different topographies, a narrow canyon, a wide canyon, with low wind, a meter per second, and then the same two canyon configurations with a high wind. And what you see in the low wind speed, and the wind is blowing in alignment with the canyon, you see a classic fire behavior shape with the parabolic shape of the fire front and a very short flanking. And with the low wind, what happens is the fire actually starts going up the steeper slope. And in this particular case, it moves up the left side here. But these fire line shapes look very similar to what was observed in the lab with a no wind case. And in the stronger wind case, similar structure, but a little bit more larger fire, and you get a larger flank size here, which then allows the fire on the slopes to spread up the sidewalls a little more vigorously. So from the lab and numerical simulations, the fire shape and growth pattern are very similar. I'd like to point out some field experiments from Portugal as well. This is the Gestosa experiment, 2001, and bring your attention to this burn plot here in the center with this very narrow canyon. So this plot is roughly 100 to 100 meters by each side with a stream bed running through it, and this was ignited at the bottom. Here's a photograph from the air. This is again provided by Professor Viegas, showing that there is strong burning all the way up to the top. Looking at the results, so this is the time evolution of the burned area and of the fire perimeter. You can see that it takes a while. It's increasing in size dramatically within the first 20 minutes, but within 20 to 30 minutes, the last 10 minutes, the burned area and perimeter increased dramatically. And this was also compared to the model that was developed from their team, and you can see that it matches pretty well with the initial time period of the explosive behavior. Yep. So real quick summary. Viegas and Simeoni summarize mechanisms of fire acceleration that have been associated with fire eruption. They went through the literature and came up with two different mechanisms. So variation of external conditions. This is changes the wind, the weather, the stability, and the fuels. And then there's the self-induced fire behavior, so spotting, gas accumulation ahead of the fire front, causing an explosive growth, and flow attachment. And so what they found in their studies is that all of these different mechanisms don't account for any one case, and it's actually more so associated with the dynamics of the fire-induced wind. Sharples et al. Also did a summary, and they summarized a bunch of trench fire cases and found that plume attachment and flame attachment was the most appropriate to describe the phenomenon for steep canyons. And this has been summarized in the document, so I don't want to go into too many details here. So in summary, from just the numerical, the observations, and the laboratory experiments, fire spreading canyons is not steady state. Both the laboratory and numerical studies have shown the role of geometry on the rate of spread. Fire eruption occurs without changes in environmental conditions. It's a common occurrence. It's mostly a result of convective feedback or fire-induced flow, similar to what I showed in the canyon photo in the very beginning of this section, and by plume attachment, where the plume and the flame actually is closer to the fuels because of the geometry. But one thing that came out of all these studies is that there is a need for more research on the topic so that fire spread models can account for this dynamic nature of eruptive fire behavior. Another unique fire spread or extreme fire behavior occurs on leeward slopes, and this has been documented by McRae 2004, Simpson et al. 2013, and Sharples et al. 2013. And so this phenomenon has been associated with lee-side vortices, or fire whirls, that develop in response to the wind flow over a slope and the coupling of the fire in the atmosphere. So here's a model simulation, and this is from a WARP-S fire simulation from Simpson et al. 2013. And so they have a background wind flowing this way, as indicated by the red arrows. Here's the hillside here. And they induced a fire that spread up the backside of the lee side of the slope here. And so that's induced by the red arrow is induced, showing the induced circulations from the fire. And so what their analysis did is they looked at the fire spread on this side of the hill with this ambient wind condition. And so basically the definition is that the fire spreads laterally across the slope. It was first observed by McRae in 2004 and called the leaf slope fire channeling, and later fire channeling. Fire spread is rapid, and numerical simulations indicate that the fire rolls or vortices develop on the leeward slope. They spread the fire laterally and perpendicular to the ambient flow. And it has also been known to be called vorticity-driven lateral spread, and we'll show you some examples of this. So here's some simulations from the WARP-S fire model. The red line here, this is at time 60 minutes, so the ignition occurred here. This solid black line is the crest of the slope, and you can see that there's a fire-induced flow against the ambient winds, which are westerly or from left to right. And so the fire line has actually reached the crest and went over. 6 minutes later, you see that there is this circulation here that develops. You see that in the vectors, surface vectors here. And so there's vorticity on the lee side of the slope that develops. And that propagates the fire front to the south and to the north. So this is how we get this lateral fire spread, or one mechanism that's proposed as why we get lateral fire spread that's fairly rapid on lee side slopes. And so if you look back at Countryman 1971, this is a classic figure where you have the ambient wind blowing over the mountain or the hill, and you have a fire-induced wind generated by the fire that's blowing up towards the crest. And so the terrain acts as an obstruction to the flow, and buoyancy generated by the fire acts to converge the nearby eddies and the vorticity, triggering the fire roll formation. And so we set a field experiment up here in Central California with very similar conditions. I just want to give you some highlights of that because it does match some of the simulations from Simpson et al. So here's the burning fire. The wind is blowing from right to left. We're burning up this grass slope. It's fully instrumented. We have the Doppler LiDAR scanning across the slope here in the right-hand panel. And so what you're seeing is the greens are flow away from the LiDAR, and the blues are flow towards the LiDAR. So you have this layer right here of real strong shear. And here's the hillside kind of drawn in over the topography here. So we have this strong shear flowing over, but later the flow enters from aloft to the surface, and this is now looking at horizontal plots. So this is the LiDAR is located here at 0, and we're scanning horizontally across the slope from basically the top left to the bottom right here. And what I want to bring your attention to is this circulation here. So this is winds at about 5 meters per second, 6 meters per second blowing towards the LiDAR, and winds blowing away. And this contour here is the actual backscatter intensity of the smoke. So this is a fire whirl. This is a velocity couplet that forms, and we were able to track this fire whirl across the slope. And we matched it with our time-lapse photos occurring here. So here's our instrument tower, here's the fire whirl, and similarly with this fire whirl here at the bottom right corner at 1945 UTC, it's a little bit smaller in size. We have a number of them here, and you can see this document at the bottom of the plot. This is the fire spread map. So these are isochrones of the fire spread taken from aerial photographs, courtesy of Diane Hall at San Jose State as part of her master's thesis. Here's the instrument array. And you can see that the fire spread mostly laterally. Because of the wind was coming over the slope, down slope here, it backed up the slope. But there is a period where we have this kind of L shape in the fire line during the instrumentation, when the fire actually moved through the instrumentation, where we had the greatest rapid spread here, or the greatest fire growth. And looking at some time series photos, the towers here, here's some arrows showing the circulations and this kind of L-shaped fire front, and the fire a little bit later converging. You get the plume developing here at 11:32:14, and different structure and very rapid motion. So from this point to here, here, and here, the fire spread dramatically. And we think that this observation aligns quite well with the numerical modeling group from Simpson et al. And Sharples et al. So it's pretty interesting that we have observations of this on a simple slope. So next, last section of the talk we're going to cover some plume structure in complex terrain, and I'm going to hand this over to Neil now. And
great, thanks, Craig. So Craig, in those previous slides, indicated kind of the presence of shear layers and inversions and the way it interacts with fires in those field scale experiments. And what we did this past summer was bring the LiDAR out to large wildfires to look at some of the interactions between fire plumes and the stratification, the structure of inversions out in the kind of wild environment. So this is an example of some plume scans that were conducted at the El Portal fire in Yosemite this past summer. I'm just going to go ahead and play this, hopefully. This is a really unique plume in that it stayed in place for about an hour and a half. And what you can see here is that we were able to resolve the turbulent structure of the plume, but also its interaction with a stable layer aloft as far as where the smoke is detraining. So this would kind of be the level of neutral buoyancy or the mean smoke injection depth right through here. And we're interested in developing a better understanding of how plumes interact with their environment, especially in complex terrain. So the case that I'm really excited about actually came from a different fire, which is the Butts fire, which was in coastal California, where we have the quasi-permanent marine layer. What you can see from this fire is two different LiDAR images. The top shows the smoke backscatter, and the bottom shows the radial velocity, where again the red is away from the LiDAR and the blue is toward the LiDAR. And we can see the presence of a distinct capping inversion, which is the top of the marine layer. Beneath the marine layer, the flow is all away from the LiDAR, and above it is all back towards it. So it's both a stable layer and also a shear layer. And these two frames from left to right are taken just 4 minutes apart. What we were able to capture here is the moment at which reaches a sufficient intensity to punch through the capping inversion and penetrate into the free troposphere above above the marine layer. And this can kind of be an important moment in inversion breakup as far as the effects on fire behavior. So we're ultimately, this is kind of in the early phases, we're trying to develop a better understanding of being able to predict these transitions. So here's another example, also in the coastal ranges of California. This is from the Bully Fire. I'm going to play an animation here. And so you can see, once again, there's a distinct inversion layer where a lot of smoke is being trapped and detraining, and I'll loop through this a couple times, but the plume occasionally reaches sufficient intensity to punch through it and then penetrate deep into the troposphere. But it's kind of varies in time with different pockets of fuel that the fire gets into. So let me play that one more time. There's a little bit of convection punching through here, but then all of a sudden, bam, we get this explosive fire growth, and then it detrains the smoke along the inversion layer when the fire loses some of its intensity. It intensifies again, and you get more plumes going through, and then you get these different inversion layers where it's detraining. And this is a photo corresponding to this sequence where the inversion layer was here. We were kind of trapped in there without much good visibility, and this is one of the moments at which the plume punched through, and it's even developing a little bit of tenuous pyrocumulus right here at the top. And we're running close to the end here. I just want to highlight some other capabilities in terms of measuring the spatial variability of smoke detraining from plumes like this. By running the Doppler LiDAR while our truck is in motion, we can kind of document where these detrained smoke layers reside and how those smoke layers follow topography. This is going back to that El Portal fire case, which was just outside of Yosemite Valley. And you can see kind of some of these spatial variations in the detrained smoke layer as it gets either trapped in valleys or advected up and over mountain ridges. We drove up and over Badger Pass twice, and the smoke was much closer to the surface in the Yosemite Valley here and here when we returned to the valley again. So just kind of highlighting some of those complex terrain dynamics that can really throw a monkey wrench into your understanding of where the smoke is going to go in a given event. And with that, I think I'll turn it back over to you, Craig.
Okay. Well, so we covered a lot of material today, and we probably raced through it a little fast, but we wanted to just highlight some unique observations that either lie outside the textbook framework. So one thing is diurnal wind systems play a role in fire behavior and smoke transport. Everybody knows that, but wanted to highlight that inversion breakup can equal rapid changes in surface winds and stability. Explosive growth, fire growth, linked to coupling of synoptic scale and mountain circulations, for example, the King Fire. We showed that the Santa Ana winds mechanically remove inversion, and the timing is difficult to predict. And so remembering that you could have zero velocity at the surface while it's blowing 15 meters per second or 30 miles an hour aloft, and within a very short period, those 30-mile-an-hour winds drop to the surface and causing increased drying and warming. We also talked about atypical diurnal flows that are possible in mountain regions, particularly the Washoe Zephyr of the eastern Sierra Nevada, and how that goes against the model of up valley, up slope all day long, where this wind develops in response to a regional scale pressure gradient from thermal forcing between the Great Basin and California, and the flows are forced up and over the Sierra Crest and down the east side. And that can really, as Neil says, throw a monkey wrench in your predictive capability. Fire spreading canyons has eruptive behavior. It's linked to terrain and fire-induced winds and the self-generated convection and fire-induced winds, as we talked about. And it's been shown in both numerical simulations and the laboratory experiments that have been conducted in the University of Coimbra. Fire eruption canyons is common. So it's not a rare event, and it should be one thing that Villegas has been saying in his descriptions and his papers, that this should be really well known to all fire managers, that it's not some rare event, that it occurs regularly, and there is capability to model it at some level. Also, atypical lateral spread can occur on lee slopes of ridges with opposing winds, and so That is another extreme fire behavior where it is generated by both fire whirls of vorticity that are formed on the lee side of hills and can spread the fire in a different direction than expected, and especially across the slope and at rapid rates. And finally, plume structure in mountainous terrain is linked to the mountain boundary layer dynamics. We showed some examples of the marine layer over terrain and how fire plumes can punch through and detrain smoke aloft and within the boundary layer, and we're still looking at these observations for analysis and linking it to fire spread rates from satellite detection tools. So with that, I'd like to thank everybody from the Fire Weather Research Lab at San Jose State University. You can follow us at Twitter at FireWeatherLab, and you can check out our research and data on fireweather.org. And I'd like to also highlight the Joint Fire Science Program, NIST, and NSF, and USDA for funding our work. So thank you, and I think we're open to questions.
Yep. First off, Craig and Neil, great job. That was a very, very well organized and clear presentation of a very complex topic, and you guys did a great job. And that's a great start to the Extreme Fire Weather Behavior webinar series. I think that sort of sets the tone for the rest. All right, so let's dive into the questions here. First one is from Kevin Mayer, and he asked, do we have enough data to recommend watch-out situations for low-level flights, i.e. to air tankers, helicopters, smoke jumpers, generalized based on time of day and in mountainous terrain?
That is a great question. I don't think we have the data. What we find, we've been on, we're in Ross. We can take our wind profiler to wildfires. We've been called out twice, and we end up going to wildfires. There is no wind profiling, and the network right now is okay. It's usually RAWs that are set up as the IMET requests it on an incident, but there's no upper level data. Occasionally you get a radiosonde on a incident, but we believe that there's a need for more wind profiling. So the answer to your question, no, there is probably not enough data on incidents for fire aviation applications and safety. Does that make sense?
Sure, yeah. Okay, next question is from Phil Dupree, and he asks, would lenticular clouds be a good indicator? I'm not sure exactly what he's referred to, but it was pretty early on.
Yeah, probably some sort of mix down or strong winds. I think the conventional wisdom is always, there's a lot of talk about lenticular clouds being indicative of strong winds in mountains, and when you end up spending a lot of time in the mountains, what you realize is that there's a lot of lenticular clouds on a lot of days, and it doesn't always mean the same thing. So like a lot of rules of thumb, they can be indicators of strong winds aloft that could potentially mix to the surface, but there's a lot of instances where they don't indicate that as well. So I think the onus is kind of on you to do a little bit more detective work in terms of, are you seeing rapid shifts in the wind at the surface? Certainly using them as an indicator, but not necessarily a deterministic predictor of what's going to happen.
Okay. Brian Potter has a comment. He says, Craig, you might point out the effect of the high frequency wave shown in the LAS on the fire behavior even before the inversion breaks up.
That's an interesting point. There's all these waves that are quite turbulent, and they're serving to mix a lot of momentum up and down, and can certainly contribute even underneath an inversion layer to variability in the fire behavior. And that's probably something that would be really interesting to look at both in models and in actual observations. So I don't think the observations exist just yet.
Yeah, that work was actually Neil's PhD dissertation simulations of inversion breakup in mountain valleys in Salt Lake Valley, and so would be a really good question and maybe a good project that we could look into further. Thanks for pointing that out, Brian.
Okay, next question is from Boyd Lebeda. He asks, are the dynamics for the Washoe Zephyr, similar to the Chinook on the east slope of the Rockies? Anything different?
Yeah, I mean, Craig's probably more of an expert than I am, but I'll take a stab at it. The Chinook wind is usually driven by synoptic scale flow. So it's driven by, for example, the passage of a trough or something that's driving strong winds across the mountains. You get that strong downslope warming. And so that's more similar almost to some of the Santa Ana events, whereas the Washoe Zephyr can actually occur, and one of Craig's slides was showing it can occur without any upper level wind support. So it can be generated entirely just by the fact that it gets really hot in Nevada during the afternoon and still cause these strong downslope winds. So it's a fair bit different than the Chinook in a lot of ways, although the outcome as far as fire behavior could probably be pretty similar.
Okay. Next question is from Nicholas Jolie. Hopefully I got that right. Asymmetric heating. Can it occur on flat terrain, such as plateaus and valleys, where a fire has burnt an area previously, producing a black fire scar and increased heating at the surface, resulting in local pressure differences and complex wind dynamics?
Yeah.
Yeah. I'll go for that one too. That's a great question. It's something I'm really interested in. There's a whole host of things that can cause smaller scale local circulations to develop near fires. So, like you said, the blackened ground can cause differences in the surface heating, and that can drive small scale breezes between different areas. And one of the things that we documented this summer are smoke breezes that develop where regions you have dense smoke shade the surface. They intercept a lot of the solar radiation, reduce the surface heating, whereas areas that don't have dense smoke are heating up much more rapidly, and that can drive circulations between those two areas. So yes, absolutely. It's a very complex environment, and I think there's a lot of work to be done to understand some of those effects.
Okay. Real quick, Gene Rogers points out the Villegas data shows the loop fire is 1996. It was 1966.
Okay, thank you.
Unless there was two. But next question from Nicholas Jolie. Eruptive fire behavior in canyons. Surely convective plume attachment associated with heated gases in the plume preheating fuels ahead of the fire, causing rapid heating of fuels ahead of a fire front in a canyon?
Yeah, it's the literature and the reviews are kind of mixed on that, but I think that's definitely plausible, and it makes sense. There are some observations from firefighter crews that see this kind of explosive nature that associated has to be with the heated gases, and preheating the fuels ahead. The plume attachment, you've got a tilted terrain, you've got a fire, and you've got entrainment from the one side because you don't have entrainment on the other terrain side, so you're pushing the flames towards the fuels. So I think the convective plume attachment is very important.
Okay. Brian Potter has another question. Yes. In the instances where the plume punches through the inversion, does it then drop back down? I can't tell from the still videos, and the video is a bit hard to tell.
Yeah, so kind of the idea of plume collapse. Most of what we've seen is that it just kind of detrains laterally, not that there is then a sudden collapse of actual downdrafts coming back through. It can kind of look like there's a downdraft, but it seems mostly like detrainment that's lateral. But that's something that I think we have a lot more work to inspect the data that we were able to collect this summer. And there's certainly it's kind of hot on our list is to be able to measure that plume collapse when you get some sort of negative buoyancy to develop, which then causes sinking back through the inversion or back into the fire, which can be a mechanism for lateral spread. And we have a tentative observation, I would say, from a fire in Northern California, the Bald Fire, that has a bit of a plume collapse dynamic that then spreads smoke out near the surface away from the fire. So it's definitely something we're going to be looking for and trying to capture again this summer when we go back out to fires.
Okay. Ryan Baker is asking about the potential for turning the simulations into fast-running, portable, real-time fire prediction tools for operational incident response.
Craig, you want to take that one?
Well, that's LES.
Yeah.
That's an LES simulation. So, this is what the fire modeling, the coupled fire atmosphere modeling community is doing, is trying to get high-resolution models for real-time simulations for prediction. So how long will it take the simulations into a fast-running portable real-time fire prediction tool? Don't know.
Yeah.
I guess throw some money at it and we'll try to do it. Just kidding. But that is actually a good question, because that's LES simulation as heavy computing power. It's similar to like running it with like the Fire Tech, which is a combustion dynamics model linked to atmospheric model. So there's a number of different modeling platforms out there, and there are people actively looking at doing this. I know Adam Kochansky at the University of Utah and Jan Mandel at the University of Colorado, Denver are actively working at getting WRF-S fire in real time.
Okay. Stephen Volman would like some more information on the Doppler LiDAR device and how it's dispatched to an incident.
Oh, thanks for the question. We are listed currently in Ross as specialist with the Tahoe National Forest. So the whole team's red carded, and once we can get dispatched, we're funded by NSF from my current grant, and we are ready to go. So you can contact me via email, and I can put you in contact with Carrie Bowers, who's she is on a hotshot crew for 10 years with the Forest Service, and she's dealing with all our Ross interactions and such, so I can get you more information on that. But we are requestable, and hope you do. Thanks.
Okay. Albert Simeone has a question. He says there's no universal explanation about fire eruptions, and as you highlighted, more research is needed. What is your opinion about the possible cause or causes triggering fire eruptions in the field?
Oh, man. Albert, that's a great question. Well, since one of the experts is asking me that question, I am a little nervous to answer, but I personally think that it has a lot to do with both the fire-induced circulations that are unique on a slope, because if you have, as you know, if you have fire on flat ground, you have entrainment from all sides. In a canyon, you have entrainment from one side, and so that helps push the flames towards the fuels. And from a classical standpoint, when you have the fuel bed above the fire, as you do on a steep slope, you're actually getting more flame impingement or plume impingement. So I do think that takes that is a major mechanism that is spreading it. Why does it accelerate as shown in the laboratory and in numerical simulations? That could be possibly the convective dynamics that have been suggested by Villegas et al. And so I don't know the answer. But I do think it's a need for research, both numerical modeling, laboratory, and field experiments.
Okay. Chris Peace asked, is there a class of the same effects on the Rocky Mountain area in Colorado? I'm not sure what he means. Maybe you guys know.
Maybe that's the Chinook wind, the downslope wind.
Yeah.
Yeah, well, the Rocky Mountains obviously associated with real severe windstorms, and the Chinook winds similar to a fern wind. So those are large scale. They're slightly different than the Washoe Zephyr, but same kind of problem. You get an ignition on a lee slope, you have a Chinook development, then you're going to be in a tight spot.
Okay. Nick Nausler asks, has there been any interest from the land management agencies of using your team with IMETs or F-bands to provide forecasts on incidents?
Where is that?
Yeah. Next one there. Yeah, we it's kind of in the works. This was our first season of actually being in Ross and being a resource that could be ordered. And on the King Fire, we were able to kind of tie in with the IMETs and provide some of our real-time data, and also have some discussions with the F-bands. And that was kind of round one. And ultimately, it would be really interesting to see much better operational support in terms of having instrumentation like this to provide real-time data for wind profiles for both. There was a question earlier about for flight operations is another big factor. Craig, I don't know if you have something more to add to that.
Well, we're trying to get more IMETs and F-bands to request us. We do want to interact with them. I think we can provide some really good data, especially with the LiDAR, and I actually think the LiDAR can calculate rates of spread because we can point it at a fire front from the flank or from the back, and we can detect where it's moving just from the smoke plume itself. So there's a lot of useful applications, not just the atmospheric side as well. But thanks, Nick.
Okay. Heidi Strader wants to know if there's any thoughts for studies in Alaska. We've got lots of interesting terrain.
We have a truck, F-250 four-wheel drive, and a couple of drivers ready to go. Just give us a request.
Okay. Sean McEldry asks, do you see a tactical application beyond research for LiDAR on large or evolving incidents to help identify or monitor these dramatic, atypical changes in winds and fire behavior?
Totally, and these are things that we have been trying to push as one of our skill sets here at San Jose State. We'd like to get multiple LiDARs on an incident to map out the wind fields. LiDAR is becoming much cheaper than they used to be, and they're getting smaller and they're more truck deployable. So Neil's going to take off real quick. I'm going to finish answering the questions. He's got to go teach advanced synoptics here. So thanks, Neil.
Yep. Thank you all.
Thanks, Neil.
Okay, so yeah, we definitely believe that there's a tactical application, especially for monitoring winds aloft for aircraft.
Okay. Wilfred Steele wants to know if, as we move forward with global warming, are we going to see impact on flow?
Well, that's a good question. Looking at local scale flows, possibly not, but at large scale flows, we see that in the synoptics and it's been predicted that certain regions will have much different weather patterns as we're experiencing around the world now. So I can't really answer that with certainty, but I know there's not a lot of work on local scale winds linked to climate change.
Okay. The next question is from Anthony Navarro, and he asks, having seen the leeward slope fire channeling from an initial attack perspective, the strong winds aloft were 15 to 20 miles per hour blowing 90 degrees to the ridge, grew to 300 to 900 acres in a short time, about 30 to 120 minutes laterally in both directions, in a closed canopy timber fuel model. Can this be predicted in some cases? If not, what is being done?
Well, I think one thing is the numerical modeling work of Colin Simpson and Jason Sharples. They are working on this phenomena with the modeling. I think that we're trying to, it's interesting that occurred in a closed canopy in timber, that the winds were able to penetrate through the canopy space and propagate the fire within the forest. So I can't answer that, but I believe that the studies that are coming out of Australia are really moving towards a better understanding of fire channeling.
Okay. Bob Easel has a comment. He says the Washoe Zephyr effect is common in the desert slopes of Southern California Peninsula Range.
Okay, good. Thank you. Yeah.
Okay. And he also has last comment, actually, or last question. It appears to me that the King Fire's explosive growth was due to the Rubicon Canyon's alignment with the southwestern afternoon winds. Comment?
Yeah, thank you for that point. We are actually doing a meteorological analysis. I have an undergraduate student that's looking at this case. We do have 3 days of wind profiles on that day, and we have radius on soundings, so we have a nice meteorological data set to investigate that. But it does look like it's the alignment with the southwest winds, definitely, because that's a very unique fire pattern. I mean, in the Sierras, you do see that southwesterly wind, even with the rim fire, how the spread was similar.
Okay. Well, that's all the questions we have. Thanks, Craig, and I know Neil's already left, but thanks to Neil as well. That was a very interesting, very clear presentation.
Great. Well, thank you so much, Josh, for hosting it and letting us test it out and getting it to go smoothly. And again, just want to say, if anybody wants to contact us, feel free to send me an email or follow us on Twitter, and we'll be out at Active Incidents this summer, and looking forward to catching up with everybody.
Okay, and just everybody else out there, if the recording will be posted here as soon as I can get it uploaded. It takes about an hour usually, and the link to that will be on the Advances in Fire Practice webpage, and you can pass that on to anybody you think might be interested. All right, thanks everybody.
Great, thanks.